Welcome everyone. I'm Christina Yasini. I'm the product lead for Ecosystem Code, and we've had a number of sessions on this product so far, and we've had some interesting and exciting developments in the past couple of months. If you have missed any of our sessions, we do have a YouTube channel where we share them. Just a bit of housekeeping. The session is being recorded and it will be shared on YouTube. Cool. So today's discussion is on closing the testing gap with synthetic data, which I think is particularly exciting if you think about the life cycle and stages that we've worked on in this product so far. So far, we've looked at what it takes to capture the right intent in building a system and how to attentively make the right contributions throughout the development process. But now we want to focus on making sure that you're fully equipped, or that your system rather, for that deployment stage and how it functions in production, and making sure that you've taken the right measures to test its functionality and capabilities in a way that provides the developer with the right context. And if there's one thing we know about AI generated systems, is that they work fast and they work with speed. And so sometimes that can cause a bit of concern when it comes to how they function in production. But if you have the mechanisms in place to be able to test the system and how it functions as a whole, then we should be able to address that quite attentively. Which leads us into the agenda for this discussion. We will begin with discussing what synthetic data actually is. And before we can talk about that, we need to understand why it matters, and to be precise of what that looks like. And most people's mental model of synthetic data tends to be thinking of it in terms of something that is made up or fake, but understanding it from the perspective of a domain model and what the intelligence of synthetic data means in the case of full stack systems is something that I hope we can cover quite in depth today. From there, we will move on to the use cases across industries, because one thing we understand is that synthetic data is not a concept that is emerging, right? It is something that has already been embedded in the operational workflows of some of the most technically sophisticated organizations across the world. And so we'll cover the role that synthetic data plays in the different stages of life cycles of a system in different contexts, and where the limits of that data exist, whether this is in the case of real world data or data that comes up in real-time context. And so it's important to understand where synthetic data is already working in building those cases, and also the trajectory of the space and where it needs to go. From there, we will understand the problem that exists with current data sources. So as we see the proliferation of synthetic data, we need to understand what is the problem, the gap rather, that it is addressing. We see that most teams already have a testing process for their systems. And so the question is whether that process is actually doing what they think it is, and what are the best ways to prepare for that at scale. So we'll talk about the 5 most common approaches to test data, production exports, handwritten fixtures, anonymized data sets, and to explain why each of those function differently in different contexts and how those structures are replicated as well. From there, we will move on to the false confidence problem, which I think is something we will cover quite in depth as not only a theoretical concept, but also a concept that has come up quite prominently in the development of AI systems, right? Where it gives you this perception functions and it works, but when it comes to actually being tested and used at scale, that's when we see a breakdown. And so understanding this at the core and being able to produce measures in place to test that is something that we will cover quite in depth today. We will then also connect this false confidence problem to its deployment dimension, right? Because we don't want systems that are just go live and then they just end up dying in that space, right? And so we want systems that continue to capture the initial intent, even in production, even when they are disconnected from the spaces or the workbench in which those were developed. From there, we will move on to bridging the gap with domain-aligned data. And this is where we move from the problem towards the solution, to understand what it means for domain-aligned synthetic data that is generated from the same ontology as the code, what it does in terms of closing the pre-production gap. And so we'll introduce the properties that make this structurally different from conventional test data, and to explain how some of the ontology that generates the code and the pre-production test data can extend into a simulation layer that calibrates the system continuously after deployment. From there, we will look into ecosystem code in practice, right? So how does into function and what are the developments that our team has made into bringing this capability to the core and to show you how it works, from capturing the intent to having that control in embedding the competence that the intent has in the different components of the system, or through pre-production with the synthetic data. And so we will cover the practical configuration, what you said, how you said it, and how the platform handles it from the first generation run to the ongoing operational calibration of the system. And then from there, we will open the floor rather to a Q&A session. So let me begin with an overview of what synthetic data is and what it means. And so what tends to happen in many of the discussions we have around this is that when most people hear the phrase synthetic data for the first time, they tend to assume that it means fake data or random data or something that is generated from a script that produces thousands of rows of lorem ipsum or random numbers. By synthetic data, we mean data that is computationally generated and is designed to reflect the statistical properties, the structural constraints, and the domain logic of a real system without being derived from real records. And by statistical properties, we mean that the data follows the same patterns and distributions you would see in a real data set. So if 80% of your customers are in 3 cities, the synthetic data then reflects that. If most orders contain between 1 or 4 items, the data follows that pattern. And by structural constraints, we mean that the data respects the actual rules of your system. So if an order must belong to a customer, every synthetic order has a valid customer reference. And if a status field can only be one of 5 values, the synthetic data never produces a 6th, which connects to our understanding of domain logic. And by this, we mean that the data understands the business rules. So if a patient cannot have 2 active prescriptions from the same medication, the synthetic data respects that. If a financial transaction above a certain threshold requires an approval step, the data reflects that workflow. So what this essentially means is that the synthetic data is produced from the functionality of the system itself, and it follows that order of events to create a workflow that is realistic to production environments and provides you with the core understanding of how it is most likely to perform in the case of having real users. And the critical distinction here is that it's derived from the omission of real records. And so this is what separates synthetic data from anonymized production data. You are generating entirely new records, model of what real data looks like, not necessarily scrubbing the sensitive fields out of existing records. And because of this, there are a number of approaches to synthetic data that one can take, right? If we're looking at it in terms of a system, there is rule-based generation, which is the most straightforward. And this is where you explicitly define the rules about the valid data, and the generator then produces data that conforms to those records. And this we see with predictable, deterministic, and useful data that is repeatable throughout different test conditions. From there, we also have statistical modeling, and this takes a reference data set, it analyzes the distributions and correlations within it, and then it generates new data that matches those platforms. And so this is a pretty strong consideration that we like to make throughout. So model-driven generation is one of the most relevant ones to ecosystem code, right? The synthetic data is generated directly from the domain model itself. And so what this means is that the entity definitions, the relationships, the business rules that are used to design the system are what inform the synthetic data. And in many cases, especially in newly generated systems, there are no existing records. So you want data that can give you the best or the most likely habits or behavior of users in that case in order to test the system end to end. And so you can think of the architecture as the scaffold and the data as the load. So what model-driven synthetic data allows you to do is to test whether the scaffold actually holds the realistic load before you put real weight on it. And because both the scaffold and the load come from the same domain specification, you're not only testing one thing against the other, you're testing the system against its own intent. And we see this particularly being important when it comes to software because it fails in the gap between the need and how it's actually built. And what model-driven synthetic data does is that it closes that gap on both sides, the side of the need and how it's built, and also on the side of the intent and the functionality of the system at the end of the day, which allows us then to move on to the different use cases of synthetic data across different industries. And I want to share this to help us understand of how this can fit into the different use cases. And because synthetic data is not something that was engineered or developed for AI generated systems. It's been solving rather real operational problems across industries for years. And what we're doing with software generation is actually the newest application of synthetic data and a well-established idea. So I just want to walk through a couple of examples of where this already exists and how it can be applied to AI generated systems going forward. So the first use case is that of machine learning and model training, which is about the data you use to teach an AI system how to make decisions. The core problem that we've seen here is that the data you have is almost never representative of all the situations that the system encounters. So for example, if you take a fraud detection model that is trained on real transaction data, has very little actual fraud because fraud is rare. And so a customer churn model that is trained on last year's behavior may not reflect how customers behave today. And so what synthetic data does, or the gap that it fills in this case, is that it lets you generate the rare events, the edge cases, the situations and the behaviors that customers have today and that haven't happened yet, right? The system needs to be able to know how to handle that, which is very important. And so for any enterprise that is building AI-driven decision systems, whether this is risk scoring or demand forecasting or customer segmentation, this is a practical necessity where the system that you're building, you want to be able to test it before you actually deploy it into production. The second case is finance, and specifically the privacy constraint that almost every financial institution operates under, where you cannot really use customer records in a development or a test environment. We have a number of compliance requirements that differ according to different countries and different markets that make this prohibitively risky. But you can also build a credible system without data that reflects real financial behavior, real account structures, real transaction patterns. And this is where synthetic data fits in, right? It allows you to fill that gap of behavior, of account structures, of transaction patterns, and generate these customer records, these account histories, these transaction flows that are statistically realistic without containing any real personal information. And the system then gets tested against that meaningful data where no real data is ever exposed or you have to worry about compliance in that case. From there, another use case we have is that of software testing, and which is quite different to the ones that we've discussed so far, in that it's mostly directly relevant to what we are covering in this session, right? And the problem here is pretty straightforward. But the test data you generate by hand is too simple and too predictable to surface the problems that will appear in production. And so what synthetic data does is that it is generated from the domain model of the system that it gives you in a test environment. And that tends to be more realistic and structural to the system as a whole. It reflects the actual entities, the actual relationships and constraints of the system without exposing any real records. From there, we have the fourth example, which is load testing. And this is more about volume rather than structure. Most systems are developed and tested at a fraction of the scale they will operate at in production. And so a platform tested with 100 of records may behave differently when it is managed by 5 million. So synthetic data allows you to generate a realistic volume and not just large numbers of records, but records that reflect the actual distribution of how real data is structured, so that your load test is testing realistic conditions rather than uniformly distributing dummy rows that no real user will ever produce. From there, and this connects to demos and walkthroughs, and this is particularly pertinent for example, roles such as product leads and consultants, where they need this in cases where they're conducting a presentation of a system to a client, or if you're in an organization where you need to present the functionality of a system to your board or a team, where you cannot use real customer data because there's a number of hurdles that one would have to cross in that case. But a demo that is built on fake records, test data, and user data that can sometimes undermine the credibility of what you're doing. It's something that is the direction you don't want to take. And so what synthetic data, on the other hand, allows you to do is to have realistic enough data that allows you to tell a coherent story and gives the demonstration the weight that it needs. The product feels real because the data inside it is real and without any of the risk that comes with actual records. And this is the pattern across all 5 of these different use cases that we see, where real data is either unavailable, it tends to be too sensitive, it's limited, or it's in cases where it's in production and you have real-time customers or you're in an organization, there's events that could happen that could really put the system to test, and you want to have this be a consideration. And synthetic data fills that gap, and the closer it is to the actual domain model of the system, the better it does that job as a whole. And for this particularly, I just want to spend a moment discussing the use of synthetic data in training large language models, because if we're talking about the use of AI in system generation, you need to understand how synthetic data fits into this in systems that tend to operate at scale and with urgency as well. And so the amount of high quality text that we see on the public internet is quite high. It's estimated to be around roughly 3 trillion tokens of data. And we have frontier labs that are consuming that data at a rate that will exhaust the usable sources within a few years. And so the next wave of AI capability cannot come from scraping just simply from the web. There needs to be a different approach that we adopt. And we've seen this with current organizations that are working in this space. We have Microsoft's 5.4 model that was trained with synthetic data as a core ingredient and not necessarily a supplement to their training, right? Their technical report states this, that it substantially surpassed its teacher model on STEM-focused capabilities, which they attribute directly to the quality of the synthetic training data. A smaller model that is trained on better synthetic data outperformed a larger model that trained on raw web scripts. So from this, we see that training a frontier model on this data also has the same level of capacity that real data has. And the cost of this is something that where training a frontier language model can cost between $100 million to over $1 billion. Synthetic data can replace that substantially by providing portions of the data acquisition and labeling cost. We have organizations such as Anthropic, Google DeepMind, and Meta that are all investing in synthetic data pipelines to reduce the marginal cost of successive model training runs. And so what this means for the individual developer that is working on building a system for themselves and wants to train it, the costs firstly are completely removed, but also synthetic data allows them to have that core understanding of how their system functions end to end. And most importantly as well is the control, right? When it comes to AI systems, you want to be able to control how it works and functions in production in a way that does not feel like you are removed from the process. And so what this does is that it gives the control to the user, it gives the control to the person that inputted the intent. And what the workbench does is allow you to deploy that intent in a production environment with the intelligence of the system embedded at the core in its functionality, in its different core components. And you are then also able to refer to that as time goes on, and you are able to capture that intent in the different environments that it can then exist.
Sorry, just before you move on from data and generated data, there is a question from Michael.
I can see it here. It says, what about generation of realistic poor quality data? In other words, data errors that are likely to occur, such as incorrectly captured ID numbers or weight measured in pounds instead of kilograms. So from there, I would like to move on to the problem that exists with current data sources and what a lot of the developers in the space are using to test their systems and why it tends to be currently insufficient. And again, it connects to this idea of control, right? When you're using AI to generate a system, you still want to have the control in your capacity. So this is one way in which this can be done. What we tend to see is that most teams rely in one of 5 approaches, and each one fails structurally in similar ways. So what we tend to see is that production data exports, they carry a privacy risk and also compliance exposure. So even when they're sanitized. That sanitization process frequently breaks the relationship between the records, meaning you are testing against data that is structurally different from what production contains. And production data reflects the current state and not the boundary conditions that are most likely to cause those failures. Another problem in this space is also handwritten fixtures that encode the assumptions of the person who wrote the code, right? So if the developer assumed that a customer always has an email address, the fixtures always include one, and the test never reveals what happens when one does not exist, right? Another example is that of static seed files, which can drift from the schema over time. New entities can be added, relationships change, and the seed files are almost never updated. And so after a few months, you're testing against data that no longer represents the system it is supposed to validate. From there, we also have anonymized data that tends to lose its referential integrity during the anonymization process. By masking customer IDs in one table but not in a related table tends to destroy the structural links that the tests depend on. And lastly, the shared staging environments can create contention and data pollution. There is no reliable way to reset a known state, and also no guarantee that another team's test run has no corrupt records that yours depends on. And so every one of these approaches share the same root flaw. The data was designed to populate the system and not necessarily to interrogate it. And so beyond these structural problems, such as getting access to real data in most organizations, this can be slow, it can be political, and it can also be expensive, where we have legal reviews, compliance approvals, data that can be siloed between departments, and the fundamental problem of working on a new product when there is no real data yet because the system does not exist. And so the best way to approach this is to have a mechanism in place that allows you to test the system before the factors of the environment come into play. And with AI-generated systems, what this creates is a sense of false confidence, right? Because if an AI produces a system in a matter of minutes, there's this confidence that it will function no matter what. But this idea can be seen as something that's inadequate because it has not been tested. And I think this is a particularly important concept, right? When a system is generated at speed and it's tested against a small amount or handwritten data and everything seems to pass, this creates a signal of readiness that is not exactly earned, where the system looks complete, right? The tests have passed, but what has actually been validated is the developer's understanding of the domain and not the domain itself. The failure modes that result are quiet, they tend to be structural, the kind of thing that surfaces weeks after a system goes live when a specific combination of conditions occur that nobody anticipated. And so the simple example here is missing data. A developer that can test a user profile page with users who all have names, email address, and profile pictures. In production, a third of users signed up using, for example, a third-party authentication that only provides the email. And so the page doesn't necessarily crash, but it can show blanks and broken layouts that erode the user's trust and silently also diminish the credibility. And from there, we also have volume, which is another factor, right? So 50 records in development or 5 million in production. These are queries that are returned in milliseconds that start timing out. And so what we've seen is that teams deploy systems where the API endpoint for listing records worked perfectly for 50 rows and brought the entire server down when a single account had 12,000 of them, because the endpoint tried to serialize everything into a single response. And this is another consideration that we need to make. From there, we also have relationship problems that are hard to catch. So for example, if every customer in your test data has exactly one order, you will never find the cascade delete that silently breaks the shipping calculation for all pending orders when a customer address is removed. From there, we also have service mismatches, and these tend to happen when two parts of a system have slightly different understandings of the same domain. One service sends an order status as confirmed, another expects processing. So during development, the test data never uses that status. In production, the first order that reaches it causes an unhandled exception. And these are things that you wouldn't catch when you see a system as functioning without actually having tested it in its different cases. And then there's also the polite data problem, where developers write test data the way reasonable people behave, where names are short, the numbers are positive, inputs are sensible, production users are not always reasonable, they paste paragraphs into name fields, they submit the same form twice, they use characters that break your CSV export. And these are valid inputs in a production system that need to be handled. And they will never appear in test data, but someone being careful to take these as potential examples is a consideration that needs to be made. And so none of these are bugs in the traditional sense, but they are gaps between the world the system was built for and the world that it runs in. And critically, none of these are purely pre-deployment problems. The conditions that cause them continue to apply and compound as the system is live. And so pre-production synthetic data catches these structural gaps. So on the left, we see is the development environment and what it actually looks like. We can have 5 to 10 sample records, relationships that are predictable and clean. There tends to be no edge cases because nobody wrote any, no concurrent activity because you're the only person using the system, and a schema that matches your assumptions because you built the schema and the data at the same time. On the right, however, is what production looks like the moment real users arrive. You have millions of records, dependencies between entities that have accumulated over time in ways nobody designed explicitly. You have nulls where your code assumed values would exist. You have duplicates from import jobs, and you also have concurrent mutations where 2 users are modifying the same record at the same time. You have a schema that is now meeting reality, which means that it is meeting all of the conditions it was never tested against. And then you have the gap. And the gap in the middle is that of the intention. It is a structural gap between 2 fundamentally different states of a system. Production data reveals what the system actually does. And this is where the failure hides, not in the code itself most of the time, but in the distance between the world the code was tested against and the world that it has to run in. And so closing that gap is exactly what domain-aligned synthetic data was designed to do. How do we deploy or enforce pre-production synthetic data generated from the same domain model as the system it is testing? And not generic synthetic data, not a library that generates realistic looking names with no understanding of your schema, but data that is produced from the actual entities, from the actual relationships and business rules that define your system. And for that, we have 3 properties. We have schema derived, right? Which is the data that comes directly from the domain model and knows your entities, your constraints, and your relationships. We also have constraint aware, where the required fields are always populated, the optional fields are sometimes null, the cardinality is respected. So you get customers with no orders, customers with 1 order, and customers with hundreds. We also have edge case rich, right, where boundary values, null combinations, and adversarial patterns are deliberately included because the absence of a constraint is information about what the system should tolerate. In the ecosystem code workbench, the domain model is not something you define separately and then hand it to the generator. It is built through how you capture your system's ontology, right? From the formal description of what your system believes exists and how those things relate to each other. And our latest development, which is the wizard, it helps you identify those core entities, define their relationships, encode the business rules, and surface the constraints that will govern the generated code. And so what you're doing at that point is not just designing a system, you're authoring the intelligence that guides every generation decision downstream. The generation engine reads the ontology I've built and produces code that reflects the intent precisely. And because the synthetic data is generated from that same ontology, the test data is testing the code against the intent that produced it and not against a separate assumption. And this is workflow continuity, right? You author the intent on the workbench, the generation engine translate that intent into a code base, the synthetic data generator translate that same intent into test data. And so the test suite runs against that data and surfaces the gaps between the intent and implementation. So you return to the workbench if you have any issues, you refine the ontology and you're able to regenerate. And so every cycle tightens the alignment between what you meant and what was built. And so the control then stays with you throughout, and the intelligence is on the platform, but the orchestration of all of that intelligence is yours. And so What this also means is that the workflow continuity is not something that stops once you go live. The ontology that generates the system and the pre-production test data can also be the foundation for the simulation layer that continues after the deployment. So for example, once the system that you've built is live, real user behavior begins to diverge from the original model in ways that are often small at first and that tend to be significant over time. And you also can see usage patterns where new data distributions emerge, business rules can change. And so the system that was correctly validated against its original ontology may drift from the real world because the real world has moved from the ontology that stayed still. And so this is where synthetic data and simulated environments come into play because they close that operational gap, right? By generating synthetic data, you create or rather enforce the simulation layer that is built on the same ontology as the system, and it generates a continuous stream of synthetic data that mirrors what the system is experiencing in production and feeds that data back into the calibration layer for the algorithms that the system depends on. And so for teams that are working with AI components that are embedded in generated systems, this is particularly important, right? You want machine learning models inside a system that do not degrade as the data is distributed or drifts from production, right? You want a simulated data that can be updated from the ontology and what allows these models to be recalibrated continuously without waiting for enough real data to accumulate. And so what we see is that synthetic data environments provides that calibration signal, and it provides the ground for truth where the two work together to create rather than replacing one another. And for enterprises, this changes the value proposition quite substantially, where pre-production synthetic data validation is about confidence before deployment. Post-deployment simulation is about sustained accuracy across the system's operational life. And together, these create a closed loop from intent to implementation to continuous calibration, and which is also what workflow continuity looks like in full maturity. And this then creates the closed feedback loop, right? Where you start with generating the system, the domain model is defined, the ontology is captured, and the platform produces the full code base. And from there, instead of immediately deploying or manually testing, you generate synthetic data from the same domain model. And this happens in the same workflow from the same source of truth, where the data knows your entities, your relationships, your business rules, because it generated from the same specification as the code. And so synthetic data then feeds directly into these test environments. And this is not manual test runs, but it's an automated pipeline that can execute against the full data set. Where those test surfaces fails, you have then found a structural gap, and being able to find that gap is particularly important. It's not a bug in the conventional sense, but a place where the domain model defines something as valid and the code does not handle it correctly. And so these gaps can be identified and fed back into the architecture. You refine the architecture, which means returning to the ontology, updating the model, and regenerating, and then the cycle begins, enforcing that control on you, the user. And what makes this powerful is that this allows for the continuous flow from the bottom to all around rather. And this is not a process you run once before you go live, right? It can be seen as a verification process that runs on every meaningful change to the domain model. Each iteration makes the model more precise, which makes the generated code more robust, which makes the test more thorough. And so by the time that a system actually reaches production, it has been validated not just against the conditions you thought to test, but against the full range of conditions the domain model defines as valid. And this is a materially different level of confidence than what most teams are working with today. And so this allows us then to have an idea of what this looks like for ecosystem code in practice. And before I hand over to Jay, I just wanted to cover this a bit, right? So what ecosystem code does, as I've said before, is that it captures the intent from a plain English description where you describe your system and what it needs to do. The wizard assists you in identifying the core ontology of that system through a structured step-by-step workflow. And then the ontology is the foundation for everything that follows. And this then becomes the formal map of what your system believes exists. And so if you are, for example, building a healthcare record system, the ontology describes what a patient encounter is, how it relates to a diagnosis, and what constraints apply to different prescriptions. And this matters for workflow continuity because the ontology does not just generate the code, it generates the synthetic data as well. And so the same structured understanding of your domain that produces the front end, the API, the schemas, the Docker configurations, or the Swagger documentation also produces the test data that is aligned to every entity, relationship, and constraint in that system. There is no separate schema to maintain. The ontology is the single source of truth for both the system and the data that is used to develop it. And so this is the direction we are building toward, all right, that of extending the ontology into a simulation layer that operates after deployment, where the same model that generates the code and the pre-production test data can power a continuous simulation environment that generates calibration data for the algorithms that are embedded in the system as the real world conditions evolve. So rather than waiting for production data to accumulate and to drift in a way that becomes more visible, you're able to test it and identify these signals proactively by generating synthetic conditions at the edge of the system's current operating envelope. And so for enterprises, this value is able to extend across the full system life cycle, where pre-production validation against synthetic data means that the architectural decisions can be evaluated against evidence rather than assumptions. And the cost of changing direction is front-loaded in the design phase instead of post-deployment simulations, which means that the system remains calibrated to real operational conditions without waiting for discrete deployment cycles. And for teams and organizations that are working in regulated industries like banking, both layers are relevant to compliance because compliance is not a one-time event at go live. It is an ongoing obligation. And so the architecture in this case is not a black box, but rather a workbench that keeps the design intent visible and executable from the first requirement to the final commit as a whole. Cool. Jay, would you like to jump in?
Yes, this is a good time to maybe show one or two things. What do you think, Christina?
I think that's a great idea.
So let me just present from my other computer. I'm going to grab the screen, okay?
Yeah, that's fine. Let me stop sharing.
Okay, so I'm not going to spend a lot of time on this, but just to kind of show one or two of the concepts. And just to note for everybody is that we will be enhancing a lot of these capabilities inside ecosystem code, as well as in the ecosystem workbench environment within ecosystem AI. And this is what the ecosystem code environment looks like. And I'll show you a particular project where the data was already generated. So this is a project or product line management system. So the concept is that you manage products, versions, and then various features for those products. That's essentially the concept. The generator, when you go to generate code, you'll notice that it shows you this, the list of your various diagrams that were generated through your specification. Your code generation, if you follow the code generation, you'll see there's no data generation per se in this environment, but you can pick the target code base. If you pick synthetic data, the way that it works today is that all of the assumptions about the data are being made for you. So here's one for Postgres, or you can generate it from Mongo. So that means that what Christina was explaining around the statistical significance of the values within a certain column within a database all get predetermined for you. So there is no, in the current version, an opportunity for you to change that. In the ecosystem workbench, when you go to data management for the ecosystem, AI product, what happens here is that it has got an intelligent backend that we will be sharing into the ecosystem code environment, where you can provide it, let's say, an existing sample data set. It will then go and infer some values from that and then generate it. And you can provide it purely through a prompt that will then use a deterministic front end that will pop up and explain to you what it's going to be doing with the data that it's generating for you. So we found that an example is that if you want to generate messaging for a certain campaign or product offers based on a certain industry that you're in, and you want to test a number of concepts, you want to be able to just describe it in English, and our intent detection engine will go pick up the intent and then present you with an option that you can use. You can also apply it if you want to, let's say in a project, generate a new project. When you describe a project, whatever that project definition is that you create, and you say generate plan, you'll see that in the generate plan, if you ask it to create sample data, this sample engine will then use our agent network to go and figure out what kind of data it must generate for the use case that you are busy designing. So that means that in the ecosystem stack, the rules around what gets generated and how it gets generated at the moment has got a level of intelligence that we are working on implementing in the ecosystem code environment. And it will give you an example of some of the details that are being used, especially if they are, let's take the classical example of a person's age. If you want to generate data like for a bank or a telco and so on, you typically find that the data will be for people between 18, like in this case, 90 years old. You can't then generate a numeric field with data between minus 50 and 20,000, whatever the number might be. You want to make sure that it's within the range of what that particular attribute realistically represents. And that is a big part of the domain and the ontology understanding, is to make sure that date ranges, ages, GPS coordinates, all of those kind of values are reliably generated for you again and again. Once it's generated, I'll just show you what I've done with the one that's already been generated. Here's just an app running in a hosting environment. So if we go have a look at it, you'll see here that it's the product line environment, and you'll see that it's a completely uniform generation distribution. So that's not typically a realistic example, but for this test, this is what we've set up. Like, we gave it the outline to say that it is for a software company and it's got an understanding of what that is. And it then generated all the data, including all of the relationships that are typically needed, that you will then be able to link if you want to link it with existing environments. So it creates the outline for you. Like in this case, there's like revisions and so on. It knows at what a version concept looks like, and it understands it. So if you wanted to do this, obviously you can do it through your own generative tools. You would have to do a lot of that work yourself. So this already has got an engine that can create that environment for you. So by the time you have a look at your data, you know that you've got basically a useful and a usable environment to start from. So I think, Christina, that's kind of it from me for now. I think we can just keep it short and sweet.
Okay, perfect, Jay. I have a couple of questions in the chat in relation to this, which I think is pretty spot on. I don't know if you want to take this one, Jay. It says from Christine, that says, what type of data is this built for example, tabular data? Also, what metrics are used to measure the quality of the generated synthetic data and its utility for downstream tasks?
So we, at the moment, generate both tabular data as well as data that can be used for messaging or for text. The text generation is not as mature. And what we found is that we used to use that for some of our own model training that we try to pull back from a little bit, but it can generate, especially in target industries where we work. So that means in gaming and insurance, in telco, in banking, in e-commerce, in retail, we can generate tabular data for any of those environments. And then the concept around the metrics of the quality is an enormous discussion, as you can imagine. And that means that do we generate, let's say that you want to generate, 1 million customers that we often kind of generate for test data. And I want for each of those 1 million customers transactions between 0 and 10,000. Let's say this is for a banking application. Then the challenge then is that, do I use graph theory to calculate, let's say, the centrality of food spending or travel spending, and let the person be more, kind of focused on a certain money personality or spend personality than another naturally? Or do we just generate the data as to what a human would normally conduct their lives by in the context of a financial journey? And we are still working on additions in that environment. So the idea would be that you will be able to, over time, add your own modules so that at least you can generate the data. And the reason why we generate the data for the ecosystem stack is to make sure that you can test recommenders and messaging and nudging and so on reliably. And the reason why we do it for ecosystem code is to make sure that you can run an application and have something that is demonstrable, that works end to end. So that means that the quality issue is quite specific to the scenario that you're working on. If you're going to train or generate data that you want to use for training, then that's an entirely different challenge, I believe, because that means then that if you wanted to train, let's say, a generic model, a deep learning model that you're going to want to share between different banks or different telcos or different companies, you then need to make sure that your key hypothesis that you want to have as part of that model is then implemented. Because then by default, you need to decide if you want the model to have bias or not. So that kind of quality is quite different than the quality of the data points themselves. The thing is, though, is that most synthetic generators, including ours, is typically by default overly correct. So that means that you won't typically find, incorrect date fields or dates or incorrect numbers and the like. So you would have to physically tell it through your pre-prompting. In our world, that pre-prompting detects the intent, and the intent will then figure out what the distribution looks like and how many incorrect values or values it need to generate deliberately. So yeah, that is a pretty big topic that you're raising. So yeah, mostly tabular. We know that the quality issue is typically too good. And for the downstream application, you need to know where it's going to be used for, just to make sure that you apply it in the right place.
Okay, awesome. And then we had a question from Michael that asked, what about the generation of realistic poor quality data? In other words, data errors that are likely to occur, such as incorrectly captured ID numbers or weight measured in pounds or kilograms.
Yes, we do have an internal tool for that we use in especially our real-time scoring engine for model serving. We haven't made it available really to clients. So we don't have a generic pure test data so that you can test validations option currently available. But you can tell it to do certain things for you. In the context of the workbench, that's the ecosystem.ai stack, but not in the ecosystem code environment. The ecosystem code environment is always going to try to generate good enough data and something that is completely validated. So there are different scenarios. But if that is a requirement, you can talk to us about that.
Cool. Awesome. I think this has been a successful session then, covering all things synthetic data and the updates on ecosystem code. I do urge you all to head on over there after the session, give it a quick whirl around, give it a prompt, a simple plain description of a system that you've been thinking of building. This is the perfect time. And then also generate some synthetic data to test it as well. Our team is also available for any questions that you may have on the workbench. You can contact us on Discord. So if you have any questions related to your system, we're more than happy to help. If you would like to also extend your use cases in the teams and organizations that you work in, please do reach out to us. We have offerings on the table that we're willing to discuss and happily to do so as well. I have shared our YouTube channel. So if you've missed a couple of our previous sessions on ecosystem code, you're more than welcome to hop on over there and catch up. This session as well will be live in the next coming days. So if you would like to go back and listen to all that we've covered in relation to synthetic data, then you are more than welcome to do so. In that case, from myself and the team, we thank you guys so much for joining us and keeping in touch. Thank you so much, Moritz and Michael, for your comments. And yeah, thanks, guys.
Thank you. Cheers.
Thanks, everyone. Bye.